Hey guys, Mr. Antonucci here, and Unit 6 is where AP Calculus gets real. It's one of the highest weighted units on the exam, and today we're going to go through some hand-picked multiple choice and free response questions, as well as cover some techniques for using Desmos on the exam. Look at the link in the description for a PDF of the questions if you want to work them out on your own. Make sure you check out the chapters in the video so you can jump around to the questions that you want to look at. Let's dive into the first problem. So here we just have the integral of secant x times tangent x. This is just a basic antiderivative rule. We know that the derivative of secant is secant tangent, so the integral of secant tangent is just secant plus c, so choice A. So here we go with the table problem. A tank contains 50 liters of oil at time t equals 4. Oil is being pumped into the tank at the rate r of t. Make sure you pay attention to the fact that r of t is the rate function, where r of t is measured in liters per hour and t is measured in hours. Selected values of r of t are given in the table above. Using a right-Riemann sum with 3 subintervals and data from the table, what is the approximation of the number of liters of oil that are in the tank at t equals 15 hours? I'm going to do a right-Riemann sum with 3 subintervals. So if we do a right-Riemann sum, the first subinterval goes from 4 to 7, and we're going to use the right endpoint. The next subinterval goes from 7 to 12. Use the right endpoint. The next subinterval, 12 to 15. Use the right endpoint. What we're actually evaluating is the integral from 4 to 15. That's going to give us the change in the number of liters of oil. But we have to keep in mind that the tank already had 50 liters in there, so we have to add the 50. So we'll have 50 plus, the first subinterval goes from 4 to 7, so that's 3 units wide. The right endpoint is at 6.2, so we're using that value. The next subinterval goes from 7 to 12, so that is 5 units wide. The right endpoint at 12 gives us 5.9. And then the last subinterval goes from 12 to 15. That's 3 units wide. The right endpoint is at 5.6. Also, if you notice, the units on the 3 would be hours, and the 6.2, 5.9, 5.6, all of those would be liters per hour, so that when you multiply these, the units end up being just liters. So if we multiply that together and add everything up, you would get 114.9. Now, one of the most common mistakes students make is they forget to add this 50. And if you do that, you would accidentally pick choice A and get this one wrong. But here we have choice C. So here we have a definite integral, and this is a common thing we'll do is you don't have to actually find the answer. You just have to set up the substitution using the u substitution that they give you. If u is equal to the square root of x, then one of the things that students often forget is to change the limits. So the lower limit is at 1, so square root of 1 is 1. The upper limit is at 4, so in terms of u, square root of 4 is 2. So on the integral, after we do the substitution, the limits are going to go from 1 to 2. This already eliminates a, b, and e. Now, if u is equal to the square root of x, then du is going to be 1 over 2 square root x dx. Notice the integral is going to be e to the u. The u is going to substitute for the square root of x, but we're not going to write it as e to the u over u because we still have to substitute this dx. So if we differentiate the square root of x, you get 1 over 2 square root of x dx. There we have the square root of x in the denominator, but we also have a factor of 2 in the denominator, so we just multiply both sides. So 2 du is equal to 1 over root x dx. And what this tells us is that 2 du is going to substitute the root x in the denominator and the dx. So we have 2 du, and this is our answer here, which is choice C. The reason they have this 1/2 here is because when you get to solve the du, you have a half there, but then you have to adjust for that. So here we have the graph of a differentiable function f. H is equal to the integral from 0 to x of f of t dt, which of the following is true. So we have a function defined as an integral. One of the things that's important to note is that h prime is going to be f of x. So this graph is the graph of f, or h prime. So we know h prime of 6 is equal to f of 6, which is just going to be 0. The second derivative of h is going to be equal to the derivative of f. So f prime of 6, well, we have the graph of f prime shows up as the slope. And at 6, the graph of f is increasing. So f prime is going to be positive, which means that h double prime of 6 is going to be greater than 0. See where we're going here. Now, h of 6 is equal to the integral from 0 to 6 of f of t dt. That would be the signed area between the curve in the x-axis between 0 and 6. Since that region is below the x-axis, it gets counted as negative, so that is less than 0. So we have h of 6 is negative, h prime of 6 is 0, and h double prime of 6 is positive. So choice A is the only one that follows that progression. So here we have the figure that shows the graph of f. Notice that f is the definite integral from 2 to x of g of t dt. Which of the following could be the graph of g? F is the definite integral of g, so f prime is equal to g of x. Now, notice that the graph of f here is linear, and it's an increasing graph. So that means f prime is going to be a constant. Since the graph is increasing, it's going to be a positive constant. So it can't be D or E or even C. It has to be A or B. Just be careful, because graph B, notice the graph is below the x-axis, so it's not B, choice A. So let g be a function with first derivative given by g prime equals the definite integral there. Which of the following must be true on the interval from 0 to 2? So we don't have a calculator to use for this one, so we have to think about what the function might look like. E to the negative t squared is equal to 1 over e to the t squared. This is always going to be positive, but it's going to be decreasing, because as t goes from 0 to 2, you have e to a higher power squared, all in the denominator under 1. So the graph is going to be similar to this. It's going to be decreasing, concave up. So if g prime is the definite integral, then the area under this graph represents the values of g prime. So since that region is always above the x-axis, g prime is always going to be positive, meaning g is always increasing. So we can eliminate C, D, and E. Now it comes down to concavity. G double prime is equal to just e to the negative t squared, which we already said is equal to 1 over e to the t squared, which is always going to be positive also. Therefore, the second derivative is positive, so g is also concave up, choice A. Notice the symbol up here changed, which means this is a Desmos permitted problem. So I'll show you how to do this one on Desmos as well as the next couple. Water is pumped into a tank at a rate of R of t, gallons per minute, where t is the number of minutes since the pump was turned on. If the tank contained 800 gallons of water when the pump was turned on, how much water to the nearest gallon is in the tank after 20 minutes? So here we have to be careful. They tell you that there's already 800 gallons in the tank, and R of t represents the rate. We want to know how much water is in the tank after 20 minutes, so we have to add to the initial 800 the definite integral from 0 to 20 of R of t dt. If this were a free response question, this would be sufficient for your work. So here in Desmos, I have entered the R of t function. This is the definite integral I want to evaluate. So we could literally type that in, 800 plus the integrals command is int. The lower limit is 0 to 20. You can literally type in R of t. Don't forget the dt. and it will give us our answer, which is 1220.149. To the nearest unit would be 1220. So we know this is equal to 1220, which is choice D. One important note is if we had forgotten this 800, you would have gotten 420 as the answer. So just, again, be careful with these problems. So here we have a particle moving along a line so that its acceleration for t greater than 0 is given by a of t. If the particle's velocity at t equals 0 is 5, what's the velocity of the particle at t equals 3? We have a situation where we're given the rate function. In this case, it's the rate of change of velocity. There's an initial velocity, and the velocity is going to accumulate from 0 to 3 minutes at the rate of what a of t is. So in order to get the velocity at t equals 3, we have to take the initial velocity and add to it the change in velocity from 0 to 3, which is the definite integral from 0 to 3 of our acceleration function. So let's hop to Desmos, and I'll show you how to do that. So I've already input the acceleration function. I know that the velocity we're looking for is 5 plus the definite integral from 0 to 3 of a of t. So we could literally type that in. Int 0 to 3 a of t dt. And then we need to add on the 5. If you do it this way, just be careful that you don't add the 5 inside the integral. Sometimes that happens. It won't calculate it. If you do put parentheses around the integrand, it will calculate it, but that's wrong because you don't add the 5 inside the integral. That's the initial velocity that's going to be added on to the change in velocity. So 11.71 is what we're looking for, which is choice E. Our rain barrel collects water off the roof of a house during 3 hours of heavy rainfall. The height of the water in the barrel increases at a rate of r feet per hour, where t is time in hours since the rain began. At time t equals 1 hour, the height of the water is 0.75 foot. What is the height of the water in the barrel at time t equals 2 hours? We're allowed to use a calculator. Since they're giving us the rate and they want the actual height, we need to use a definite integral. Here I have the rate function directly in Desmos. Now remember, the height was already 0.75 feet, so we need to add that to the definite integral from 1 to 2 of the rate function. And you get 2.111. So coming back over here, that would be choice D. One more honey is poured through a funnel at a rate of R ounces per minute. So we know we have the rate of change where T is measured in minutes. How many ounces of honey are poured through the funnel from 0 to 3? This one we have to be careful because they did not give us an initial amount that was already poured. We just need to do the integral from 0 to 3. So we have to integrate the rate to get the total change. So I have the rate function in Desmos. Again, just type int, and we'll go from 0 to 3. R of t dt, and you get 7.429. And that corresponds with choice D here. Okay, so now we have our first free response question. No Desmos or calculators allowed on this. The figure above shows the graph of f prime, the derivative of a twice differentiable function f on the closed interval 0 to 4. The areas of the regions bounded by the graph of f prime in the x-axis on the interval 0 to 1, 1 to 2, 2 to 3, and 3 to 4 are 2, 6, 10, and 14 respectively. The graph of f prime has horizontal tangents at 0.6, 1.6, 2.5, and 3.5, and it's known that f of 2 equals 5. We want to evaluate the definite integral from 0 to 4 of f times f prime dx. Free response question here. First thing we need to do is figure out what the antiderivative of f times f prime is. We could use u substitution. So if u is f, then du is going to be f prime of x dx. So we could rewrite this as the integral of u du. Now I didn't change the limits, so I'm not going to put them on there. The antiderivative of u is 1/2 u squared, which is going to be 1/2 f of x squared. And then we're going to evaluate that at 0 and 4. That's the little trick to this piece. So you do 1/2 times f of 4 squared minus f of 0 squared. F of 4 would be the accumulated signed area up to 4 on the graph. Well, we know this first region is 2, then this region is 6, the next region is 10, and then the last region is 14. The 6 and the 14 get counted as negative. I'm going to write my answer up here. So we have to figure out f of 4. F of 4 you can think of as the region from 2 to 4, because we know f of 2 is 5. So we would have 5 plus 10 minus 14, which is equal to just 1. We would have 1/2 times 1 squared minus, now we have to get f of 0. So we can use the fact that f of 2 equals 5 to help us here. Here's how we do that. We get the definite integral of f prime from 0 to 2. That's got to be equal to 2 plus -6 because of these two regions, but it's also equal to f of 2 minus f of 0 by the fundamental theorem of calculus. So I know that this has to come out to -4. I also know that f of 2 is 5, so I would have 5 minus f of 0 is -4. And this means that if I solve for f of 0, that would be 9. So we could substitute that in for f of 0, 9 squared. So 1 squared is 1, 9 squared is 81. Subtract, you get -80. Divide by 2, this will come out to -40. Now, for the work with this, they're really only looking for that you have the correct antiderivative with the function squared, and that you have the correct constant of 1/2 there, and then the final answer. All the other work that I showed would not gain or lose points for this particular question. So here's our next one with no calculator. The graph of the differentiable function is f is shown for -3 to 3. The graph of f has horizontal tangent lines at x equals -1, 1, and 2. The area of regions A, B, C, and D are 5, 4, 5, and 3, respectively. Let g be the antiderivative of f such that g of 3 equals 7. Let h be the function defined by h of x, which is 3 times f of 2x plus 1 plus 4. Want to find the definite integral of -1 to 2 of h of x dx. We know that h is equal to 3 f of 2x plus 1 plus 4. So we could start with that. There we go. We can break this apart. We can separate the plus 4 into its own integral and factor out the 3 from the f. It's pretty straightforward to get the integral of 4. That's just going to end up being 12. But the f of 2x plus 1, we got to use u substitution. So u is 2x plus 1, du is 2 dx. But we have a 3 out front, so to adjust for that, we're going to multiply both sides by 3/2. So then this integral becomes 3 times the integral of f of u du plus 12. Now we need to substitute the limits. The original limit in terms of x was -2. If u is 2 times x plus 1, then the new lower limit is going to be -3. Forgot the half there. And then similarly with the upper limit, if you plug in 1 in terms of u, 2 times 1 plus 1 is going to be 3. We can just get the accumulated signed area of the regions A, B, C, and D, multiply by 3/2, add 12. So we would have 3/2 times the sum of region A, which is 5. Region B, the signed region, would be 4. Region C is 5, that's positive. Region D is 3, which is negative, and then plus the 12. If you add all that up, you get 25.5. There you go. For this problem, you would get 2 points for using the fundamental theorem of calculus correctly here, and then another point for the answer. So here we're allowed to use Desmos for this one. The height of the water in a conical storage tank shown above is modeled by a differentiable function h, where h of t is measured in meters and t is measured in hours. At time 0, the height of the water in the tank is 25 meters. The height is changing at a rate of h prime, meters per hour, for 0 to 24. First question, what is the minimum height of the water during the period 0 to 24? Justify your answer. Now, for this part, since we have a closed interval, the absolute minimum would either have to be at a critical point or an endpoint. Since we're allowed to use the calculator or Desmos, it's important that we write down the correct information for credit on our work and then perform the calculations on the calculator. The first thing we want to do is figure out when the derivative is equal to 0. They already give us the derivative, so we're really just solving h prime of t equals 0, and we'll use Desmos to do that. All right, so I've graphed the function in Desmos. Now I want to note that f of x is the graph of h prime of t. If you type in h prime, it's not really going to work because you didn't have a function h there to begin with. So I just know that f is the same function as h prime. Also, I restricted the interval so that I'm making sure I'm only looking at the correct point. Critical numbers occur when the derivative is 0. You can just click on the graph there, export it to your list, and then we know that the derivative is equal to 0 at that value. So t would be 6.261. So that would be our critical number. The next thing we need to do is evaluate h of t at the endpoints. H of t is going to be equal to 25, which is the initial height of the water in the tank, plus the change in height, which is the integral from 0 to t of h prime of x dx. Now notice I changed the variable to be x in the integrand so that my upper limit is t, which matches the variable for the function. I can use this in Desmos to find values of h. What I'm going to do is make a little table of values here, and I'm going to go at 0, 6.261, and 24. Then I'm going to evaluate that definite integral as a function for those three values and then compare. So here's how we would do this. We could let h of t literally equal 25 plus the integral from 0 to t of f of x dx. And then you could literally type in h of 0, which gives us 25, h of 6.261, and h of 24. So we can see that the minimum occurs when t is 6.261 and the height is 16.339 or 16.338 meters. So you would write out the minimum height is 16.338 meters. So you'd actually get 4 points for this question. 1 point is showing that h prime equals 0. Consider that and get the t value. Second point, using the fundamental theorem of calculus where you write h as a function defined with a definite integral. Then you get the absolute min value. And this is sufficient for justification. This is called the candidate's test. Then the second part, the line tangent to the graph of h at t equals 16 is used to approximate the height of the water in the tank. Using the tangent line approximation, at what time t does the height of the water return to 25 meters? So an equation for the tangent line, we could just use point slope form, solve for y, which would be y equals h of 16 plus h prime of 16 times t minus 16. We could say that this is our tangent line approximation. And then this is essentially asking us, when does that equal 25? So here back in Desmos, we already have the h function there, so we could do h of 16. And h prime of 16 is just going to be the function f evaluated at 16 as well. So we would have 23.496 and 1.196. So then our equation of the tangent line would be 23.496 plus 1.196 times t minus 16. And then we set that equal to 25. The easiest way I know how to solve this equation equal to 25 is graph the line y equals 25 as well as the tangent line. Just be careful here. You see that they intersect at 17.257. So you could literally show this y equals h of 16 plus h prime of 16 times t minus 16 and then write the equation underneath it because you've already defined what h is. In the previous part, I erased the work so you don't see it. And then you set that equation equal to 25, and then you could literally have t equals 17.258. And that would be your answer and that's it. This problem was worth 3 points. You have 1 point for the value of h of 16, a point for the equation of the tangent line, and a point for the answer. Here's one more graphing calculator permitted question. We have a table of values. On a certain weekday, the rate at which vehicles cross a bridge is modeled by a differentiable function r for 0 to 12, where r is measured in vehicles per hour. So notice it's the rate. And t is the number of hours since 7 a.m. Notice also that t equals 0 corresponds to 7 a.m. Values for capital R for selected values of t are given in the table. Use a midpoint sub with 3 subintervals of equal length indicated by the data in the table to approximate the value of the definite integral from 0 to 12 of r of t dt. Indicate units of measure there. So for this one, you are allowed to use Desmos. Totally fine. The definite integral here, this is pretty straightforward, standard question. Definite integral from 0 to 12, r of t dt is approximately equal to. It's important that you put the approximately equal to. Now we've got to do a midpoint method with only 3 subintervals. This sometimes trips students up, but if you do your first subinterval from 0 to 4, the midpoint would be at 2. The next subinterval is going to go from 4 to 8. Midpoint is at 6, and then 8 to 12, midpoint is at 10. Notice the width of each of those intervals is 4 units wide. So you could do 4 times r of 2 plus r of 6 plus r of 10. Now there's no special tricks in Desmos for this one. You would just literally do 4 times the quantity 3653 plus 3010 plus 1986, and that's going to be 34,596. And the units on this would be vehicles, because the 4 right here is the change in time. That's the width of the interval, which is in hours. And then these are of 2, 6, and 10 are vehicles per hour. And when you multiply that out, the units come to vehicles. This one was worth 2 points. You get a point for setting up the midpoint sum. You can't just write the answer down with the correct units. Although that does give you the second point, you do need to show the midpoint sum setup. So it's important to write the definite integral down, the approximately equal sign, the midpoint sum, and then your answer. And that's Unit 6 in the books, guys. If you found these multiple choice and free response questions helpful, hit the like button. Make sure you subscribe for when I publish new videos. And also look at the link in the description for a PDF of the questions if you want to work them out on your own.